The Science Show featuring this week Carl Smith's final report on our energy futures.
But what about the sun? Its energy drives just about everything down here on Earth. If Australia is to transition away from using fossil fuels, solar power would certainly feature in our energy mix. And we already have the technology to cheaply transform the sun's rays into electricity.
Yes, so when I turn on the hot tap, almost all of the hot water that comes out is heated by the sun. Only in winter is there a bit of boosting if I don't have a lot of sun over a particular week.
Professor Andrew Blakers, Director of ANU's Centre for Sustainable Energy Systems.
It won't be solar electricity if I cook at night, but of course I will have produced enough solar electricity, exported that back to the grid, that I can borrow some back. So when I first came to this house, all of the light bulbs were the old style incandescent light bulbs. I switched them all over to compact fluorescence.
We're at his home in suburban Canberra, which runs on 100% solar electricity.
Well, we're going upstairs in my house to have a look from my balcony at the solar systems that I have and that my neighbours have. So we have a solar hot water system that's available for producing the hot water that runs the house. And both my neighbours have inserted photovoltaic electricity systems on their roofs, and this is for production of electricity. And I also have one on my roof. You can't see it obviously because we're directly underneath it, but I have about a 3.5 kilowatt system. That's enough to provide about 130 or 40% of my annual electricity needs. So each year I get a cheque from my electricity retailer. I don't actually have to pay the retailer.
So over a year, this Canberra household produces more electricity than it uses. And there are many more homes just like it.
Canberra's actually a little bit below average. The average penetration of solar around Australia is now about 1 in 6 houses. Canberra, it's about 1 in 8. In Adelaide and Brisbane, it's about 1 in 4. The simple reason for that is that solar is so much cheaper than getting electricity from the grid.
You're listening to Energy Futures on The Science Show. I'm Carl Smith. This week we're looking at solar power, starting with rooftop photovoltaic panels.
Those rays of sunshine, or photons as they're called, hit slices of silicon. Silicon is the second most abundant element in the Earth's crust, and it's turned into thin discs of material.
And this silicon is in the panels as a semiconductor, isn't it?
That's right. Silicon's a semiconductor. It's the basis of both the photovoltaic industry and also the electronics industry for logic circuits that go into every computer and every mobile iPhone and everything else. So these silicon wafers are about 156 millimetres across and about 0.2 millimetres thick. And a ray of light comes in and knocks an electron off one of those silicon atoms. And this electron wanders around within the silicon, and if it crosses the p-n junction just underneath the surface, it's like a one-way membrane. So the electron can cross it in one direction but can't come back. So you get a trapped negative charge on the surface of the wafer, and therefore there's a positive charge balancing on the undersurface of the wafer. And so if you connect the top of the solar cell to the bottom of the solar cell through a load, like a battery, then you can get electrical current out of that solar cell. And that's the way that photovoltaics works. No moving parts.
The technology has been around for decades, and NASA was among the first to use solar panels to power satellites in space.
As scale went up and costs came down, the scale of the industry has just continued to rise and rise and rise. And the scale of the industry has grown by a factor of 100 in the last 12 years. And the cost of the early solar panels in the 1960s were 1,000 times greater than the cost of the panels that we can buy now. And there are enormous cost reductions and scale increases still to come in the solar industry.
Has efficiency changed a lot?
Efficiency in manufacturing goes up by about 0.5% a year or so on average. The early panels were maybe 6 or 8% efficient. Current panels are in the 17-18% efficiency, and you can buy panels in the 21-22% efficiency range now. The efficiency in this context means of all of the energy in the sunlight, say 1,000 kilowatts per square metre at noon, if it's a 20% efficient panel, you'll get 200 watts of electricity. And that is gradually creeping up. It'll top out at about 24-25% because of the fundamental limitations on efficiency for the silicon basic panel. But there are a lot of tricks we can do to make silicon even more efficient and to bypass these fundamental limitations. The most efficient solar cells now are 46% efficient, but these are designed for operating at the focus of 1,000 sun solar concentrators, where you use lenses or mirrors to concentrate the light 1,000 times onto very small and very expensive but very efficient solar cells. However, they haven't really been able to crack the market yet. The market is still overwhelmingly bog standard silicon solar cells.
And how long is their lifetime?
Well, the typical lifetime of a solar panel, guaranteed, is about 25 years. The guarantee is that after 25 years, you'll still have at least 80% of your starting efficiency. So the degradation is about 1% per year, which is really rather small. They're going to last even 30, 40, 50 years in a dry location. Near the sea, you can get corrosion and metal contact, so it doesn't last quite as long.
About ongoing maintenance, repairs?
Maintenance is essentially nil. Some people choose to wash their panels, not rely simply on rain and dew to clean the panels. And you can get maybe 5% more power over the course of a year if you wash your panels. But otherwise, people typically just leave them. And after about 10 years, you need to replace the inverter, which converts the direct current from the solar panel to alternating current that can be used by your devices in your home and also be exported to the grid. So there's very little maintenance, and typically it's of the order of 1% per year of your initial expenditure.
And the price for installing these, has it come down significantly?
Yes, the price of the panels has come down by a factor of 5 since 2009. There's been a dramatic reduction in the cost of the panels. The cost of installation is now about 2/3 of the total cost of your system. And part of that is the transport, the mounting rails on your roof, and part of it is the inverter and power electronics required to interface with the grid. As a very rough approximation, the panels might be 1/3, the physical installation 1/3, and the power electronics probably a little bit less than 1/3. There are substantial opportunities still for further cost reductions in all three of those components, and so it's my expectation that the cost of solar will continue to decline gradually for at least another 10 or 15 years, and will end up much cheaper than any alternative.
And Australian government modelling predicts solar PV will emerge as the cheapest form of energy generation in the country by about 2040, overtaking wind power.
Wind and photovoltaics are by far the front runners of the renewable energy revolution. In 2013, more than half of all new generation capacity around the world was hydro, wind and photovoltaics. Everything else was the other half, including all of the remaining renewables and nuclear, oil, coal, gas. In China, it was 3/4. So there has been a very, very important tipping point. The majority of new installations now are photovoltaics and wind, with hydro about to be passed by both of those. Looking ahead in the 5 to 10 year range, most installations will be photovoltaics and wind. And the important point about both of those technologies is that they are distributed. They're generally not in very large power stations such as with coal or nuclear. There are millions of wind generators and hundreds of millions of solar panels distributed everywhere. And this is leading to a complete revolution in the way in which we generate energy and retail it. In particular with photovoltaics on building roofs, not just houses but also light industry and commercial buildings, in order to save energy for the companies and the householders. This is leading to a very substantial reduction in the purchase of electricity from the grid, in particular during the course of the day, which is when the generators used to make most of their money. So fossil fuel generators are under very great commercial pressure, and the pressure is only going to increase.
But what about reliability of that energy supply during cloudy periods or storms?
The first point I'd make is that this has been talked about a lot, but it's been over-talked about. South Australia is now getting 40% of its annual electricity from wind and photovoltaics. And South Australia has no hydro to balance that. Hydro is really good at balancing it because you can go from no energy output to full output in less than a minute. South Australia is weakly connected through a high voltage grid to the eastern states, and it stands on its own to a very substantial degree. But nobody noticed the fact that South Australia has gone to 40% intermittent wind and photovoltaics. The grid is stable, the system works, the electricity continues to be supplied to everybody. When we get to the 50 to 100% range, we will have to deal with this issue, and there are a number of ways. The first is that we stop moving loads from day to night. For example, off-peak electric water heating will take place during the day, not during the night. We will make ice, we will cool, we will heat during the day rather than at night. The second is that we will manage loads. There are many loads that are interruptible, and that can mean that if we suddenly have the cloud come over the sun, we can simply interrupt a load rather than have to draw on a storage. When we deal with storage, there are two aspects. One is predictability. Solar and wind are both very predictable on every timescale from seconds to years. So we will know from satellite observation and ground observation when there's going to be a wind lull and when there is going to be a lot of cloud. And we have these wind and PV systems distributed right across the continent of Australia. So only continental scale wind lulls and cloud will affect the generation system. And for that you have storage.
Currently, solar generates about 1% of Australia's electricity. But it's grown quickly, with capacity increasing tenfold over just 2 years from 2009 to 2011. That growth has been driven by homeowners.
I think the resistance has largely vanished. The fact is that 1.4 million houses, that's about 1 in 6 of Australia's housing stock, has a solar photovoltaic panel on the roof, and a significant number more have solar hot water systems on the roof. I think the penny has dropped for most people that solar is a way to save money as well as reduce the generation of greenhouse gas emissions. And one of the really nice things about having 1.4 million solar homes, 4,000 megawatts, is that most people now understand what solar's about.
Andrew Blakers. Solar power has huge potential in Australia as an alternative energy resource. Not only is the technology available and accepted, but the costs keep coming down. What's more, Australia has the highest solar radiation of any continent. In fact, the solar energy hitting Australia each year could power the country for 10,000 years. Even if you just look at flat sites within 25 kilometres of existing transmission lines that aren't in national parks, there's still enough radiation hitting those areas each year to power Australia 500 times over. In 2015, the vast majority of Australia's solar power, more than 4,000 megawatts, comes from rooftop systems. But commercial solar farms have also begun appearing. One of the largest operating in the country is the Royale Solar Farm, south of Canberra.
I'm Laszlo Csányi from FRV Services Australia. We are the developers of Royale Solar Farm, just 25 kilometres out of Canberra CBD. It's a beautiful day, cool and sunny, and we are surrounded by approximately 81,600 solar panels. We generate enough electricity here to power about 4,500 Canberra homes.
It's a very big development. Rows and rows of solar panels set on rolling hills, right on the ACT's southern border. But even larger farms are operating or are under construction around the country.
It's completely safe to touch. It's exactly the same technology what you would be seeing on a residential house anywhere in Australia. And they're about as big as a person, about 2 meters tall and about 1 meter wide.
These things are producing a certain amount of energy, but how much energy went into making them, and how long does it take them to pay that off?
Very quickly. These panels generate the same amount of energy which went into creating them. You look at about 3 years only, and these panels have a lifetime of 20-25 years plus. Studies show that in 2013, all the solar industry, so all panels produced around the world, have done more good than actually what went into creating them. That's very significant. We have an industry which actually produces more energy than what is actually used to create it. That's a very important thing about solar. And as we earlier said, you don't need any fuel. The only fuel you need is the sun. There's no water usage, there's no fuel, nothing. It's just sun.
How big an industry is large-scale solar, so solar farms here in Australia at the moment? How does that compare on a global scale?
It is quite small, unfortunately. FRV alone identified many sites in Australia which are more than capable of supporting large-scale solar farms. This is approximately over a gigawatt of capacity now, which is 1,000 megawatts of capacity, could be developed in a very short time frame.
The Royales solar farm is set amongst some beautiful countryside. There aren't many homes nearby, but the panels are covered with anti-reflective layers, and extensive visual and glare assessments were conducted before installation.
Generally, the community response is amazingly supportive of all these solar panels and all these solar farms. Neighbours located near the solar farms are generally accepting to these solar farms, these developments, and some consultation needs to be done. And that can be anything about from the visual impact to glare. As long as the consultation is done and countermeasures are taken, there's no problem with these systems. They go through a rigorous development approval process.
But such a massive array does change the look and feel of the valley in which it sits. Hey, Jennifer. Jennifer Hallett's heritage-listed home, Green Gables, looks out across the Royales solar farm.
I don't mind solar power. I think it's great. It's just that it's right in my backyard, so to speak, and the glare sometimes is really bad, and the view's not all that crash hot either. And so there it is, and you can see I'm working on trying to put trees in, and I'll put another row of trees closer to the house here to try and block out the view and the glare.
So what do we see?
Well, we're seeing rows of grey panels with tracks in between them. At the moment, the sun hasn't started to set too much, so the glare is only at one end of the farm, but as it sets, it gradually increases to this northern end, and that's when it's at its worst. It looks like a white, shiny lake with the sun on it. We were happy to have it, but just not right up against the houses.
You're listening to Energy Futures on The Science Show. I'm Carl Smith. This week we've looked at rooftop solar panels, and we're now exploring the emerging commercial solar farm industry. Unlike other technologies we've examined over recent weeks, the rows of panels at the Royales solar farm just outside Canberra don't have any moving parts. Although Jennifer Howlett isn't impressed with the view, there isn't much else to worry about. More than 80,000 fixed panels just sit in the field, absorbing solar radiation. And how difficult were they to install? Laszlo Chani from FRV Services.
Very easy. Many people compare it to Meccano sets. It is basically just putting steel into the ground and putting more steel on top and just putting the panels. And this is mainly manual labour.
These structures that you've installed here, how sturdy are they?
Very sturdy. Of course they have today. They're about as tall as, well, they're a bit taller than a person, the framing at 30 degrees, which means there's wind loads acting on it. They have to survive all that. But the panels themselves are really, really sturdy. They test these panels by dropping steel balls on them to emulate hail, and they can easily survive hailstorms as well. It's very rare that you see panels breaking. On the positive, if it does happen, it's extremely easy to replace the panels as well. They're all modular. You just have to unplug the panel, get the new one, put it on the railings and tighten the bolts.
How do you keep those tops clean?
Most of the cleaning is actually done by rain. The biggest issue probably is bird droppings. As you can see here, they're pretty clean. And I'm not sure when we had the last decent rain, but they look pretty clean, and over about 15 degrees angle, you achieve pretty good self-cleaning properties thanks to rain alone. On a big plant like this, you want maximum output pretty much all the time, and therefore in the operation and maintenance contracts there's usually a requirement to clean these panels. Of course, that's also good for local employment. It employs people, but other than that, the operation and maintenance of solar farms is incredibly cheap.
What other, operational maintenance costs are there? I saw there was a couple of you guys down in the maintenance room, but how many people have to run a 50-hectare, 80,000 panel site?
Not many at all. 1 to 2 persons, plus occasional labour. Again, just to clean the panels. Running of the solar farm is just supervision and monitoring and really seeing if there's any faults. There's nothing in them to break down. As you can hear, well, you can't hear, there's no noise. There's no fuel requirements. The only fuel you need is the sun. And therefore there's no transportation requirements, there's no waste. And these solar plants are very easy to coexist, just on fields like this in the middle of Canberra.
Do you see solar, both rooftop and the big commercial ventures like this, being competitive just on a base level with some of the other energy resources by, say, 2040?
Earlier. I would think earlier. And it's purely because other prices going to go up. There's unknowns around transportation cost when you're transporting fuel. With solar, you don't have that. And that's very important as well. It's hard to tell what's the future, but the future looks really bright for solar in general, as long as there's incentives in place, and just like subsidies for fuel and fossil fuel sources. Incentives are required, but on an unsubsidized level, solar is already competitive.
In factories around the world, the silicon wafers and panels are being mass-produced. Andrew Blaker's lab at the ANU looks at ways of improving that technology.
The trays hold silicon wafers. They're pushed into the furnace, which sits at about 1,000
After a tour
degrees
to
or
see the
1,000
process of making solar cells, we made our way to his office. I asked whether he thought the large-scale commercial solar farms, or rooftop solar, would emerge as the leader in photovoltaics.
I think it'll be roughly half-half. It's obviously more expensive to install a photovoltaic system on a roof. However, the soft costs are much lower. By soft cost, I mean the cost of raising finance, which involves engagement with insurance companies, equipment procurement providers, finance providers, and the like. With a roof-mounted system, you ring up a company, they do a Google Earth search of your roof, work out where the solar panels will go, and that's it. There's no finance to be worried about. Everything is streamlined and smooth. So the reduction in soft costs in roof-mounted systems is an important parameter. A second is that competition for roof-mounted photovoltaic panels is not against the 5 or 6 cents per kilowatt hour wholesale electricity price. It's against the 30 cents per kilowatt hour retail electricity price. And this is a very, very attractive proposition for roof-mounted solar, which is why it's taken off in the domestic market and will go to 70 or 80% over the next decade or so of all houses having solar panels. And the big coming market is in fact commercial and light industrial buildings, where the company wants to substantially reduce the cost of electricity to itself, and it does it using roof-mounted solar panels.
There are other emerging ways to use solar radiation to make power, but they're much more expensive than solar PV.
Within the wider solar industry, photovoltaics is about 90 to 95%. There is a relatively small component from solar thermal electricity. Solar thermal electricity is produced using mirrors that focus light onto a central receiver. Typically, it would be a receiver mounted on a tower that might be 50 metres tall, and a whole host of heliostats, as they're called, directing the sunlight up to that tower. Each heliostat is 15 or 20 square metres of highly reflective mirror. The receiver gets very hot, and you can run water through it, which gets converted into steam that can then drive a turbine in much the same way as a coal-fired or gas-fired power station. The situation at the moment is that photovoltaics is considerably cheaper than solar thermal. Solar thermal has a significant future, hopefully, in high-temperature processes, for example, in the metallurgical industry, and also has a future in terms of the ability to store heat for a few hours in the form of molten salt, and hence to provide a little bit of storage within the grid system.
And still in the experimental stage are technologies such as thin film solar and organic solar, which could see solar panels applied to surfaces other than rooftops. Some groups are even looking to move away from the standard silicon model.
Within the photovoltaic industry, silicon is about 85 to 90%. Most of the rest is a material called cadmium telluride from a company called First Solar, and then everything else together is just a few percent. Everything else includes organic solar cells and amorphous silicon. Many people have announced that their new technology is going to supersede silicon. Silicon photovoltaics has become a juggernaut. It's a very big industry. It's got sales at a system level of the order of 100 billion per year now. It's allied with the integrated circuit industry, also based on silicon, which has got sales in the $500 billion range per year. There's no particular reason why silicon would ever have to be superseded. There's unlimited silicon, there's unlimited raw materials for photovoltaic modules. It's what the Earth's crust is made of. It's impossible to run out of them. That said, you can never discount the possibility that some new material will come along which will turn out to be much cheaper and, importantly, more efficient than silicon. And if that's the case, then good. It just means that photovoltaics will enjoy yet a further acceleration of cost reductions.
Regardless of the materials used, the process of tracking the sun is also being optimised, with some arrays tracking east to west and others also tilting across the north-south axis.
Hitherto, large-scale solar farms in the 10 to 100 or even 1,000 megawatt range have been fixed in the ground. So frames are constructed and the panels are bolted onto the frames and the panels just sit there. Increasingly, or majority I would say, of new large-scale photovoltaic farms, the panels are mounted on a one-axis tracker, which is a very long beam running north-south, and in the morning it faces east, during the middle of the day it faces directly up, and in the afternoon it faces west. It just rolls over once per day. And you get 15 to 20% more annual energy from a roll tracking system. It costs maybe 10% extra, so you end up with a 5 to 10% overall cost reduction.
Andrew Blakers, Director of ANU's Centre for Sustainable Energy Systems.